that brings us to solution stoichiometry. Stoichiometry is just going to come back around and around and around, and it's always going to bring dimensional analysis with it. So this is why molarity is such a useful unit in chemistry, because in the chemical reaction we're concerned with how many moles of this to how many moles of that. We're always doing this moles in the middle. So now, this really is, we can still start with grams to moles to moles to grams. But in a question like this, instead of a mass in grams, they're going to give us a volume and a concentration. So we're going to take the volume and use the concentration to find the moles. And then at the end, the moles will use the concentration to find the volume at the end. And of course, there's lots of different variations on that. So we're just swapping those out for volumes. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? Now, when we look at the numbers here, we've got a concentration and a volume and a concentration and another volume. Those were the same kinds of numbers we had in the dilution problem we just did. Are we diluting anything here? No. This is a chemical reaction. We've got a chemical equation here. This is the concentration of one substance, and that's the concentration of a different substance. Don't use the dilution equation because you're not diluting something. We need to use stoichiometry because we're doing a chemical reaction. So again, let's use the equation to organize the information. So I've got the concentration of the nitric acid, so that's 0.150 moles per liter. And I'm told I have 35.7 milliliters of sodium carbonate, and its concentration is 0.108 moles per liter. And I'm trying to find the volume in milliliters of the nitric acid. Stoichiometry. Start with grams to moles to moles to grams. I have two pieces of information about this substance, and I have one piece of information and a question about that substance. So this is the one we're starting with, and that's the one we're finding out about. So here, do they give me a mass? No, they don't. But they give me a volume and a molarity. So if I had the liters, I could convert that to moles. At the end, they're wanting us to give it in milliliters, but I can convert from moles to liters and then to milliliters. We're going to do that little shortcut here because this is in milliliters, right? But what does milli mean? 1 times 10 to the minus 3. So 35.7 milliliters is the same as 35.7 times 10 to the minus 3 liters, because milli stands for times 10 to the minus 3. So that saves us a fraction. Thank you. So liters to moles. This is liters of the sodium carbonate. And then I'm going to moles of the other thing, HNO3, and then I'm going to liters of HNO3, and finally to milliliters of HNO3. Liters to moles to moles to liters to milliliters. Liters to moles to moles to liters to milliliters. This guy up here is the key to the whole problem. I put my units in there so that they're going to cancel out, and then the units tell me where to put the numbers. So those liters cancel, moles cancel. Of course, there are other ways to solve this problem. But, you know, when a child first starts moving around, they walk before they learn how to skip, right? Or dance. And so this is like walking. This is the sure way. It works every time. Once you learn how to do this, to walk, then you can learn how to skip. And you can skip things and make it shorter. But we have to understand how it works first. Moles per liter, that's my molarity. Sodium carbonate, this is the sodium carbonate, 0.108 moles per liter. 0.108 moles per liter. Mole ratio, where does that come from? Not the periodic table. Equation. Right. So 1 mole of sodium carbonate reacts with 2 moles of nitric acid. So 1 mole of sodium carbonate, 2 moles of nitric acid. Here I've got moles per liter. That's molarity again, but this time moles is in the bottom. The concentration is 0.150 moles per liter, and so the 0.150 squeezes in down there. And then at the end, so, you know, if we step back from this, we can see, well, this times 10 to the minus 3 is going to cancel that one out. But it's okay to do them too. 35.7 EE minus 3 times 0.108 times 2 divided by 0.150 divided by 1 EE negative 3 equals. All the numbers they were giving me had 3 significant figures. So 51.4 milliliters of nitric acid. And look, we didn't have to calculate any molar masses. Any questions? 1.4. There's another one. Consider the reaction 2A plus B makes C. What's the limiting reactant if you mix equal volumes of a 1 molar solution of A and a 1 molar solution of B? Well, if the concentrations are the same and the volumes are the same, they don't tell us what the volumes are. They just tell us that they're the same. What can we say about the number of moles of A and B that are being put into this reaction vessel? They're the same, right? The concentration is the same, and the volume is the same, therefore the number of moles have to be the same. So we can deduce from that that the moles of A added is equal to the moles of B added. The chemical reaction tells us I need 2 moles of A for every 1 mole of B. So if I have equal amounts of A and B, which one's going to run out first? A. Because I need twice as much of this, right? So then A is the limiting reactant. Those are tricky because they make it hard to do, just do the math. Some people get really comfortable. Just give me numbers, I'll calculate it. Don't make me think about it, right? But this is just, let's stop and think about what's happening here. Does anybody have any questions?